All right. So, how's that homework going? I noticed some of you already turned in your 1, 2, and 1, 3. Any questions about any of that stuff from chapter 1?
I have a question on the homework, 2, or a couple, 2F and 6A on 1.2.
Okay. I'm going to go ahead and pull up the homework here so we can look at it. I'll share my screen. All right, so in a second here, you should be able to see my screen. All right, so can you tell me again, JP, which one? It was 2, which? F?
Yeah,
Okay. And then the other one was which?
6A.
6A. Okay, so let's look at 2F first. So 2, it says we want to verify that the function is a solution of the differential equation. And so how are we going to do that? How would you actually show that that's a solution or verify that that's a solution? What are they asking us to do?
I'm not too sure.
Can anyone else
take their
help?
respective derivatives and then plug it back into the original DE?
Yeah.
Take
yeah.
the chunks. Take the chunks that are required in the original differential equation and use the parent function.
Yeah. So here's our y, right? I got it highlighted. So what we're going to do is you're going to take the derivative and the second derivative, and you're going to go ahead and put those into this differential equation.
Okay.
And hopefully once you do the algebra, it ends up giving you the exact same thing on this side. So that's what it means to actually confirm. So real quick, guys, I'm going to mute everybody because I'm getting some background conversations. Feel free to unmute yourself so that you can say stuff if you want, but this way we have less traffic in the background. Anyway, so yeah, this is just a matter of take a derivative, take a second derivative, plug it into the respective places and see that it simplifies down, right? Whenever you're confirming a solution or verifying a solution, no matter what kind of equation, it's the same kind of thing. I mean, think about like if I gave you a quadratic equation and I said, does this point satisfy it? You would just plug it in and check and see if you got equality. That's not the same as actually trying to solve it. So anyway, oh, thanks, Mikey. No worries. All right, so is that better for the approach there for 2F, JP?
Yeah, that's fine.
Okay.
I just didn't know where to start, essentially.
Okay, and so the other one was 6, which one?
A, the last
6A.
question.
Okay, so it's virtually the same idea. We're going to start with, you've got your y equals x squared times 1 plus natural log of x. So you'll differentiate it, take the second derivative, and you're going to plug them into this differential equation right here and make sure that you actually get equality, right? But then where this one's a little bit different is we also have some initial conditions. And so for these, what you need to do is show that if you take e and you plug it into this function, you get 2e squared. And then when you differentiate and you get your y prime, when you plug in e to that formula, you get 5e. So that's just ensuring that we're finding the one function that actually passes through this point and has a slope of 5e at that location. So this is really just a lot of algebra. After you get the derivatives, you just punch them in and simplify and see that you get the same thing. All right, so better?
Yeah.
Yeah, okay. Other questions about the homework? Well, then I'm going to stop sharing here and we'll just go back to everything. So Trey just shot out for 6A. Did you get 0 for the constants? Yeah, no, maybe. I can't tell you, Trey. I didn't actually do the problem, so I don't know what the C's end up being. All right. Okay, any other questions? All right, well then let's just kind of recap what we did last time. So last time we went and we found the solutions to any linear first order differential equation. So we have the nice little patterns. For the homogeneous is just that we integrate the p of x, we make a negative, take e to that power, and there you go. And then if they were non-homogeneous, we had to start with the homogeneous. We called that y1, and then we multiplied it to an unknown u, right? And then we found that u by following the same process, right? And so it's kind of nice. It's just really procedural, but it does get a little bit boring, probably. All right, so we're feeling pretty good about linear first order. Thumbs up, thumbs down. Yeah, thumbs up, mostly. All right. So what we're going to look at today are what we call separable differential equations. And we actually made use of this a little bit last time. But let's go a little bit deeper and talk about what separable really means and how this is going to allow us to deal with things that are not first order. So I'm going to go ahead and switch to the board here. So let's look at separable differential equation. So separable means that we're going to be able to write these guys in the form h of y times y prime equals g of x. So I did mean to have a y here instead of an x in this function. But these are ones that we're going to have y's, obviously, and we're going to have x's, but we can move all of the y's over to the side with the y prime. And then all the x's can be moved to the other side. And if we have this, the reason that these are nice is that what we can do if we make that y prime a dy dx, we can fire that dx over to the other side here. And this turns into an h of y dy equals g of x dx. And now both of these sides can be integrated. So what we end up finding then is this new function of y is actually equal to some function of x. And that gives us our solution. So these are super nice just because the process is fast. And it goes back to just regular old integration. We don't have to do any kind of tricks. There's no, let's multiply by some unknown u and find it. None of that. We can just dive right in. So notice that the linear first order homogeneous were examples of separable, right? Like if we go back to those that we looked at last time, where we had y prime plus p of x times y equals 0, these things are all linear. We are exactly of this form. If we move things around, we end up getting 1 over y times y prime equals negative p of x. So 1 over y would be our hy. The minus p of x is our g of x. But we are ready to go and we could integrate. And in fact, you can see now where that solution comes from, right? We get that p of x, we have to integrate it, make it negative, and then it ends up being e to that power because 1 over y gives us a natural log. Right? So the stuff we did last time, at least the homogeneous bit from linear first order, is a special case of separable. But what we're going to do today is we're going to talk a little bit more about what about the broader case, what about some other examples that are not linear. They're all going to be first order. We're not going to have any second derivative, but this is going to open us up to a lot of other kinds of differential equations that we can solve. So let me just show you some examples, and along the way we'll talk about some of the issues and some of the things we have to watch for. hopefully you're going to find this section pretty easy, because after the algebra step, it turns into just regular old calculus, regular old integral stuff that you did last year. The hardest part is going to be doing the integrals, except I know that you guys are going to use something like a calculator or Desmos or something like that, which is totally fine. But obviously you're going to use whatever the techniques necessary depending upon the structure. All right, so let's look at this guy. Let's say we've got y prime equals x squared over y times 1 plus x cubed. All right, so this thing is separable. Right now it's not in the correct form, but all we have to do to get it into the correct form is to multiply the y so that we can move it over onto the other side, so that we get y times y prime is equal to x squared over 1 plus x cubed. All right. So now it's just a matter of doing the integrals. So let's see what happens. Now I'm going to not do this anymore because I'm tired of rewriting it. The y prime, I'm not going to split it into dy dx to move the dx. We know at this point we just need to integrate, right? So save ourselves a little bit of time. We're just going to jump straight to let's integrate this thing. So the y, that's going to give us y squared over 2. What are we going to get on the other side? You recognize what that integral is going to be? Without the use of technology.
You got to use u sub to do it.
Yeah, so it would be u sub. And notice that the top is almost the derivative of the bottom. It's just off by a third. So that tells us it's going to be a natural log. So if you do the u sub, you're going to get, if you let u equal 1 plus x cubed, you're going to get a du over u with a constant 1/3. So it's going to be a natural log. It's 1/3 the natural log of 1 plus x cubed. Again, technically, we need absolute values in there, but for most of our situations, that's not going to be an issue. When you apply this to something, it's very rare that what you're plugging in are actually negative, because most of the time when we're doing differential equations, these are with respect to time, and we don't usually go backwards in time. All right, the one thing though we need to make sure we put on is the plus c, because there are lots of possible solutions, and that gets us there. All right, so no big deal, right? But obviously, you probably want to go ahead and solve this for y. That's not too bad here. We just move the 2 over, take a square root. And so we're going to get y equals the square root of 2/3 natural log of 1 plus x cubed plus c. C is inside the square root. Be very careful here. I know that we get in the habit of just sort of putting that c on at the end and all that. We need to make sure we put the plus c in before we do algebra, because if we were to put that plus c outside of the radical, that's very different than that plus c being inside the radical. So just watch out for that. All right. However, there's a bit of an issue here. Anybody spot it?
Plus or minus.
Yeah. When I take that square root, it's actually a plus or minus, and so I have 2 possibilities. That's a bit of a problem. Why is that a problem? And I don't mean the forgetting part, because let's just put it in there. This is still a problem. Anybody see why? So I got a couple of shoulder shrugs. West 2. No, it actually has nothing to do with the natural log. I mean, the natural log will be an issue for x's. right? There's going to be a restriction on what x's we can plug in because of that natural log. However, that's not the problem. The problem is legit.
Is it because if x is -1, you get 0 on the denominator in your original function? Does that have anything to do with it, or is no?
No, that's still kind of the issue that shows up with natural log,
Okay.
right? Because if x is -1, then that makes it a 0 inside of the natural log, and we know that 0 is not in the domain of natural log. So
Okay.
that same problem we saw up here
Uh-huh.
still shows up, but it's legit. The problem is the plus or minus. All right, well, I think I've tortured you enough. The problem with that plus or minus is that when you have, what we're looking for is a function that satisfies the differential equation. And when we put a plus or minus, it's no longer a function. Because think about how functions work. You plug in an x, you only get one y. There is no option. And even in the wording that we use, plus or minus, we actually have two different choices. So you've seen this before when we did implicit differentiation. I'm going to switch to me so you can actually see me instead of the board. So when we did implicit differentiation back in the day, do you remember that one? That was the whole, if you had some sort of an equation that you didn't necessarily solve for y, you could still differentiate, and you kind of just assumed that y was a function. You didn't necessarily know what it was. And that let us deal with things that weren't functions themselves. So even something as simple as a circle, right? You know the equation for a circle, x squared plus y squared equals a squared. That thing we could still differentiate implicitly. We would get it in terms of x's and y's, but that way we could treat it all as one object instead of breaking it into the upper half and the bottom half. And those would have been the plus and minus, right? For like a circle, if you solve for y, you'd get the positive square root of a squared minus x squared. That's the top half. And then you'd get the negative square root, and that was the bottom half, right? So what it does when we take the square roots and stuff like that and get our pluses and minuses, it's really breaking this thing down into functions. So what we had on the board here, the plus square root business was one function and the minus was the other. So when we do this, when we have separable differential equations, we will often get to a point where it may even be impossible to solve for y. So it's totally fine to leave them as implicit expressions. We pretty much go to explicit when we have a initial value. So if there's an initial value, then we know for sure which part we're on, and I'll show you that here in a second. But as it is, we're going to go ahead and leave them usually in the implicit form. So I'm going to go back to the board. And I'm going to show you what I mean. So this second line to the bottom, is one that I'm going to put the arrow by. This is the implicit form. Obviously, you can do things like multiply by 6 to get rid of the denominators or whatever. But this is implicit because we don't actually have it solved for y. But we still know that whatever the function is going to satisfy this. So when you square that function and divide by 2, you're going to get this expression on the other side. Okay, so we're usually going to leave it like this. And like I said, this bottom one, we're really going to use this one for the initial value problems. And we're going to be able to determine from that initial value which one we want, the plus or the minus. It's basically going to be, take that circle example, which half of the circle is it on? Is it on the top half or the bottom half? All right. This obviously isn't a circle, but it's the same kind of idea. Do you want to be on the positive side of it or the negative side of it? The initial value will tell you, and we'll pick accordingly. All right. One other thing that I want to talk about before we step off this is the x's. So that's come up a couple of times, like when I asked the issue, remember West 2 in the chat box put something about the He's like, it's something about the natural log, noticing that was going to be an issue. And then Mikey also, when he went back to the very beginning one, said, oh, x can't equal -1. So we've got a problem there. So if we had an initial value problem, and in fact, let me give you one. Let's turn this into an initial value problem. We're going to have the same differential equation, but this time, let's have an initial value of y of 0 equals -1. So if we were going to solve this initial value problem, we would have done exactly what we did. We're going to go through and we're going to find this solution. Let's just start with the implicit solution and see what happens when we're at our point. We're going to be able to figure out what that C is by plugging in 0 for x and -1 for y. So let's do that. We'll get -1 squared over 2. That's going to equal 1/3 natural log of 1 plus 0 cubed plus C. So 1 plus 0 cubed is 1. The natural log of 1. Anyone remember natural log of 1?
0.
It's 0. Log of it. Any base log of 1 is going to equal 0. So we get 1/2 is equal to C. So in our implicit form, we can go ahead then and write that as y squared over 2 equals 1/3 natural log of 1 plus x cubed plus 1/2. All right, but now since it's an initial value problem, I actually want to know what is y. Let's get y equals. So we'll go ahead and solve this for y. I'm going to write it above, just so that you guys can catch up on this if you haven't gotten it yet. But we'll multiply by 2, and then we'll take a square root. So we get y is equal to plus or minus the square root of 2/3 natural log 1 plus x cubed plus 1. So notice how that C is gone now compared to what we had done before. We know the C is actually equal to 1. But we can also answer which one is it? Is it the plus or the minus? So which one is it? Is it the plus or the minus? You got a 50-50 shot. How about thumbs up for plus, thumbs down for minus? All right, so Wes gave me a thumbs down. Trey and Josh gave me a thumbs up. I have a lot of not really sure. Oh, I got a couple more thumbs up. Got all kinds of thumbs up. So it looks like Wes is the only -1. Everybody else is positive. Are you positive that it's positive? All right. It's actually the negative. So Wes was right. Surprise, right? Surprise, surprise. Wes actually got this one right. It's actually the negative. So I'm going to pick on you again, Wes. Why the minus?
So if we plug in 0 into the function, we get the negative square root of 1, and that gives -1. But if we did positive, then it would have been 1 instead of -1.
Exactly. Go back to the initial value. Remember what we needed is that when we plugged in 0, we had to get -1. And the only way we can ensure that we get the negative is by putting the negative out front. So that's what I meant by the initial value problem is going to tell us which one we're going to need. And that's why, in general, if all we're going to do is find the group of solution, what we're going to do is just this, get ourselves to the implicit form. But when we have the initial value problem, we usually go ahead and bump ourselves a little further and go to the explicit form because we know something about that function. We know a point that we're going through. And so we can run back and get that. All right. So are we good? Does that kind of make sense? So that's just sort of one of the things we're going to have to watch out for when we go with these separable. All right. Oh, other thing to notice is very little of our discussion here was actually about calculus, right? The only thing that we actually talked about was algebra kind of stuff. Oh yeah, but this brings back let's talk about the X issues as well. So we notice that even from the very beginning, even before we actually solved it, there are some things that we know cannot happen, right? And the X equaling -1 is one of those things, right? Mikey brought that up in terms of just the algebra division by 0. When Wes brought up the natural log, that's an issue as well. So we know that X cannot equal -1. What else can you tell me can't happen here?
Y can't be 0.
Yeah, Y cannot be 0 for the same reason. It's going to cause division by 0. So we also know that Y cannot equal 0. So some things that we definitely have to watch out for. The Y not equaling 0 is actually going to be taken care of by this expression. Like if you were to graph this, you're going to see that Y doesn't equal 0. It's not going to happen because there's also going to be a restriction on our X's. So if you were to think about the real number line, somewhere on here is -1. We know that we cannot be at -1. And so any interval of our solution is going to be one side or the other. We're not going to be able to like jump from one to the other. So my question to you is, with this initial value problem, which interval do we get? Do we get the -infinity to -1 or the -1 to infinity?
-1 to infinity.
All right, it is the -1 to infinity, and you can see that for a couple reasons. First, if you just look at the form of this differential or of the solution, we know that the natural log has to be bigger, or the stuff inside has to be bigger than 0, and that's going to force us to be on the other side of -1. I am going to warn you to be careful with that argument, because remember the technically was absolute values around that when we integrate. And then if we have a negative number, it's perfectly fine. And that would be this interval on the left. But more importantly, what tells me that I need to be on the right side is the same thing that told me we had to have the negative. It's our initial value. If you look at where we were when we actually found the solution, we were looking at when X is equal to 0. Well, 0 is already on that positive side. So not only do we know this solution, we also know that it's going to be good on -1 to infinity. All right, so there's that guy. Pretty basic, not a lot of integration. Integration was pretty easy, but kind of a deep question. I mean, there's a lot we could talk about there. All right. Ooh, we have a guest. Mike's got a cat who's joining us. All right. So here's another one. Let's look at this guy. This is another one where the differential equation itself is not very difficult. We're going to get the solution pretty quickly, but it does have some interesting stuff to talk about. All right, so let's go with y prime equals y squared over x. And let's see if we can solve this. And then we'll put on an initial value and we'll solve that one. And we'll talk about some other issues along the way. So first things first, is this separable? Everybody's nodding their heads. Yes, absolutely it is. It's actually really easy to get there. We get y prime over y squared is equal to 1 over x. All right, So in the context of what we had written, what I had written for separable, h of y is 1 over y squared, and g of x is 1 over x. All right, so let's go ahead and integrate both sides. The 1 over y squared is going to give us a minus 1 over y. And then the 1 over x is going to give us natural log of x. And we'll go ahead and put on our plus c. So solving for y, we're virtually there. And we get y equals minus 1 over the natural log of x plus c. So super quick, super easy. All right, so some things we can talk about right now before we even go to an initial value problem or anything like that are similar things. We got the natural log when we integrated. So technically, absolute values. And we also see that x cannot equal 0. Go back to the original differential equation, we're dividing by x. So since x cannot equal 0, we know we're going to be on one side or the other. And that's what happens with those absolute values. If we're on the positive side of 0, this is perfectly fine. If we're on the negative side, we would have our absolute value. All right, so cool, no big deal. But here's the deal. There's also another solution to this differential equation. There's another solution that is not of this form. And this is when all of you should start being concerned. Right? You should be concerned here. Hold on, I want to look at you guys. So you should be concerned here because we went through the process. We separated, we integrated both sides. Like that's how these things work. And yet now you've got me telling you, yep, but there's another solution that we've missed. So I knew West 2 was going to get this. If you look in the chat window, he just wrote y equals 0 with the question mark, because you know how he is with the 0. Well, yeah, y equals 0. That is the other one that we're missing. Let's go back and look at that equation. So if we look at this equation, if y is equal to 0, y squared over x is 0, and the derivative of 0 is also 0. So not only is this a solution, but also y equals 0. All right, so how are we going to know when we've got one of these other ones? Well, really, the only other solutions are going to be trivial solutions, the ones that are kind of, well, yeah, duh. Y equals 0 is a duh for this equation. We're not used to looking for that at first. So it might take a while for you to try to catch those. But we definitely need to be careful and see if those obvious solutions were caught or not. And sometimes they are. Like what we end up with at times when we solve these things are going to be such that, like in this case, let's say it was y equals 0. It's going to be such that when we plug in for c, there's going to be some value of c that would actually make it work. Like what if, obviously this is not the solution to this differential equation, but what if we had solved this to be c over natural log of x? In this case, y equals 0 would be in this. It would be the case when c is actually equal to 0, right? Or what if it had been c plus 1 over natural log of x? This still would have caught 0. 0 would happen when c is equal to minus 1. So watch for those. Watch for what are the obvious solutions, and see if those obvious solutions actually show up or not. But that conversation about missed solutions and all that really only happens when these are initial value problems? Because if it's an initial value problem, let me go ahead and change this back to what it actually was. If it's an initial value problem, we're going to know if it's the y equals 0 or not. So let me amend this to be an initial value problem. So we're going to go y of 1 equals 2. So not only am I looking for a function that satisfies this differential equation, but I'm requiring that it goes through the point 1, 2. All right, well now we know we can go ahead and cross off y equals 0. Because y equals 0 does not go through the point 1, 2. So we don't have to worry about that. So that's what I mean by when you have an initial value problem, a lot of those ors, if we have multiple possible functions, are going to go away because initial value problems bring us to the one function that works. So if we want to find out what that one function is, we just plug in the 1 and the 2 and let's see what we get. So we have 2 is equal to minus 1 over the natural log of 1 plus c. Natural log of 1, of course, is equal to 0. So this tells me that c is equal to minus 1/2. So we just found then that the solution to this initial value problem is this guy right here. Now, if it were me, I would probably just go ahead and multiply top and bottom by minus 2 to get rid of the fraction and stuff like that. But whatever algebraic equivalent you get is the algebraic equivalent you get. All right, so another one that the calculus was really easy, but there's some things that we have to watch out for. So let's just sort of recap what we have to watch out for. So look for the following. First, look to see if there are any things that are going to cause problems. Look for the x's and y's that we can't have that could cause division by 0 or domain issues and things like that. Keep that in mind because that's going to be kind of important later when we talk about where these solutions exist and what values we can plug in. Right? Also, be careful when you solve for y. If you get into an explicit form, make sure you've got the part that is actually correct and works, right? So make sure you've got that. And then also look for other possible solutions. And those other possible solutions are going to be like really basic functions. They're going to be functions that are pretty much like constants, right? That are all, you know, y is always 1. It's identically 1 or it's identically 0 or things like that. Those are going to be the ones that you might lose, that you might not catch. So watch out for those because they actually matter. All right, so how are we feeling so far? No big deal? Differential equations is easy, right? Well, I mean, so far, it's not going to get that much worse. Just the algebra and some of the calculus techniques are going to get a little more complicated. So speaking of more complicated calculus techniques, let's try this one. So let me give you this differential equation. It's going to be y prime equals k times y times L minus y. And some of you may recognize this. If you do, don't say anything yet, no spoiler. But some things I just want you to know. Both k and L, these are constants. I'm just not specifying what they are yet. We'll talk about what they actually mean for this applied problem, because this is actually an applied problem. It comes from an applied problem. All right, so separable. You should all be nodding your heads. Yeah, this is definitely separable. I mean, there aren't even any x's. So all we have to do to separate this is just move all that y stuff over here. And we get y prime over y times L minus y equals k. So now let's integrate. Integrating the k is going to be easy. That's just going to give us a kx, all right? What about this side? What are you going to have to do with those y's? And don't tell me, put it in my TA89. What integration technique do you have to use? Parts is not going to do you any good. But Brennan, yeah, decomposition, the partial fractions.
Partial fractions, yeah.
Yeah, so this guy's a partial fractions problem. Just the real quick reminder of how that works. Since you've got a couple of factors, you would make it a over y plus b over L minus y. You go ahead and build that up. So you would get a times L minus y plus b times y. And what we need to do is figure out the values of a and b that would make this top equal to 1, because that was the top of the fraction over here. And there are a couple ways of going about it. You could actually just set up the systems, like if you distribute through, you would get like the constant part, a times L, that's going to have to equal 1. You're going to get minus ay plus by, that's going to have to equal 0 because there are 0 y's. The other way you can do it is by plugging in L or plugging in y, 0, because if you plug in L, this piece goes away and you're left with LB, that has to equal 1. If you plug in 0, that's gone, you're left with LA, that has to equal 1. But regardless, you go through this process, we break it apart, and what we end up with is 1 over L times 1 over y plus 1 over L minus y. And this we can integrate. We can even fire that L over onto the other side since it's a constant and just kind of lump it in over there. But what we'll get is the natural log of y minus the natural log of L minus y is equal to KL times x plus c. So hopefully whatever piece of integration technology you like to use, when we integrate this side, should give you something that is at least equivalent to this. The L might be over on this side or something, but there's our integral. Okay, so cool. There's a good old implicit form, but I want to go ahead and solve for this explicitly. Let's get a y equals, because I want you to see what that looks like, because we're going to go ahead and graph it and stuff like that. All right, so what we're going to do, we've got a subtraction of logs, which means we can put those together as a division. So we're going to have the y over L minus y. Since that's in a natural log, I'll get rid of that natural log by doing e to the power over here. So we're going to get e to the klx plus c. And I hope you guys are all good with me just putting that c out front, because the plus c means we're multiplying by e to the c, which is a constant. And now this is going to be pretty quick, because we can multiply to get rid of that fraction. So we have y is equal to LC e to the KLX minus y times c e to the KLX. I move this other piece with y. I go ahead and I factor. I'm going to get y times 1 plus c e to the KLX. Sorry about that. My phone buzzed, and I think you guys all heard it because I heard it in my earphone. But now I just divide by this guy. And you notice that this is starting to be not so terrible. And I'm actually going to do one more thing. I'm going to divide each of these pieces by CE to the KLX. It's going to just make it a little bit nicer looking. We're going to get L on top. On the bottom, we're going to get a 1. That was from this guy. I'm flipping him. 1 plus CE to the minus KLX. Right? When I divide the 1 by e to the KLX, it gives me a minus KLX. And the other thing you need to know is that this C is not the same C as we had before. It's actually 1 over that. But if it's an arbitrary constant, when we divide by an arbitrary constant, we get another arbitrary constant. So we're good to go. Whew. All right. But there it is. There is the solution to this differential equation. All right. So what made this one worse, obviously, was the algebra. The calculus technique of the partial fractions, obviously, is what it is. But who am I kidding? You guys are all going to use something like Desmos or whatever to get it. All right. So let's talk about this one, though, in terms of what about other solutions? Because there are other solutions. So you remember what I told you we need to look out for? We want to look for other functions that are probably, constant functions that are identically some number that could potentially be solutions. So go back and look at the original differential equation. Let me erase some of this just to get it out of the way. We'll go ahead and leave what we found as a solution down here. Does anybody else see a solution to this differential equation that's not this ugly guy? All right, so Thea was just giving me this.
0.
What about y equals 0? She beat Wes to the punch on this one. Is y equals 0 a solution? Obviously, if we plug in y equals 0 over here, we're going to get 0 on the right side. What's the derivative of 0? Also 0. So it turns out that not only this one, but also y equals 0. There's another one. Can anybody else see another function, y equals, that will be a solution? I'll give you a hint. It's another constant function.
Is it L?
All right, so let's see. Wes 2 just threw out y equals 1. Thea just said, is it L? It is one of those. All right, so Brennan just gave me a L sign with his fingers. He just went like that, yeah. So it absolutely is L, because if y is equal to L, if y is a constant, what's its derivative? It's 0. And notice that if we plug in L for y, we're going to get 0 times other stuff, which is still 0. So we also have y equals L. And let me just rewrite this one up here. So y equals L over 1 plus c e to the minus KLX. But what I want to know is, are either of these of the same form as the one that we just calculated? Are there values that we can plug in for c that will make this thing equal L or equal 0? Because if there are, then we don't need to write them separately, right? Because then they're a specific case. So let's look at L. If we want just y equals L, that means we need the bottom over here to equal 1. Well, if we want the bottom to equal 1, that means this exponential piece has to equal 0. And the only way we could make that happen is by letting c equal 0. So since 0 is a perfectly fine choice for c is anything we want, right? So since that's one of them, we don't actually have to write y equals L as a separate case. That's actually included here. This is what happens when c is equal to 0. All right, so no special notice for that one. We just, it's there, but we know that it gets incorporated. Okay, what about y equals 0? Is there a c value that will make y equals 0? So come back and look at this. We've got this fraction. Is there any number you can plug in for c that will make that equal 0? Well, the answer is no, there isn't. This is a fraction, and the only way a fraction can equal 0 is if the top is equal 0, and the top is not 0, it's L, right? So this one is a special case. Some people look at this and go, yeah, but what if like this grows incredibly large, so we let c go to infinity or something like that. But infinity is not a number. We have to specify a c. And even if we let c equal Googleplex, right, 10 to the Google power, it's still not equal to 0. It's very small, but it's not equal to 0. So long story short on this one, we don't have to write y equals L, but we do need to make sure that we include the y equals 0 as a possible choice. But if I gave you an initial value problem, then we know which one we're going to be in, because we're either going to go through a point where the y is equal to 0, or we're not. And if we're not, then we're in here. Does it send us directly to y equal L? Well, maybe. We'll find out. It would, through the process, it'll get us a c equals 0. All right, so how do you feel about that one? I mean, it's algebra, but we see what's going on, and you can see these things we have to look out for. All right, so here's my question. Anybody recognize that? Has anybody seen that before? I see Brennan's nodding his head. I think he's typing something in.
Isn't it something to do with inductance? Because I see the L.
It's not inductance. That L is a different L.
Got it. Okay.
But Brennan just put max carrying capacity. And yeah, this is what we call logistic growth. And this is one of those when we have a population that's growing, but there's a maximum number that they can actually reach. If they get to that point, it flattens out. If they get above it, they die off until they reach it. We call that the carrying capacity, right? And you can actually see this in the equation. And you can also see it if you plot the vector or the slope field. And we'll look at that. We'll plot the slope field. And then we'll also look at what happens when we choose specific values for our initial conditions. But this is called logistic growth. So let me write some stuff on the board, and then I'm going to share with you my screen, and we'll look at the slope field and talk about that. All right, so this is called a logistic growth. And we use this for population modeling. It's much more appropriate than exponential growth, because any animal, any object that's, or any living creature that's growing, there's going to be a maximum number. You can't have an infinite number of humans on Earth. You can't have an infinite number of bacteria cells. Eventually the resources are limited, and there's a maximum number. And that's what that L is. L, we call it the carrying capacity. And think of it as the maximum number. So I'm going to put here maximum population. And this is going to be determined just by the environment, the resources. If we're talking about the coyote population in Lake Tahoe, there's only a certain amount of space, certain amount of food for them to eat, things like that. And so there's going to be a maximum number, right? You're never going to have 1 million coyotes in South Lake Tahoe. It's not going to happen. So there's going to be some sort of max. So that's what the L is. And then the K, this is a growth rate. I probably shouldn't put equals because it's not necessarily the growth rate, but it's related to the growth rate of the population. So how many more we're going to get and that kind of thing. So if you look at this equation real quick, you can kind of see why this does what it does. If I ignore the L minus Y, like if I just cover that and I have Y prime equals KY, so just this piece, you may remember from our discussion last time that that gives us an exponential, right? That was the most basic linear first order homogeneous that we solved. And we saw that we got e to the KT, right? So that just gives us exponential growth. But when we throw on that L minus Y, we're saying that not only is the growth or the change in population dependent on how many there are, but also how far away we are from that carrying capacity. That's what L minus Y is telling us. It's the difference between the maximum number and our current number. And so if those are really far apart, so if we have a very small population, we're still able to grow. This is going to allow this to be a bigger multiple on Y. So it is going to kind of grow exponentially. But as we get closer to that carrying capacity, L minus Y gets smaller, which decreases our rate of growth. Right? All right, so that's logistic growth. But let's do this. Let me go ahead and share my screen so that we can actually see what this looks like in terms of a slope field. So I found a nice little slope field generator. I basically just Googled slope field generator and it brought me to this site. It's actually a Desmos macro that was built by somebody. Hopefully it pulls up here soon. Okay, there we go. All right, so there's our slope field. I'm going to my other audio so you can hear me a little better. All right, so you notice that right now, this is not actually the slope field that we're interested in. What I've got graphed, this was just the one that I think popped up when I pulled it up. This is the slope field dy dx equals x over y. So over here, you can see the different slopes. So like at a specific point, I can even move this point around, right? So if I take that guy, oops, left click, not right click. So I just move that somewhere. Never mind, it's not letting me do it. It actually projects the slope field or the slope for that point. I don't know why it won't let me move it. Nah, whatever. But these are the slopes for the various points. So for example, if we go to -1, 1, you plug in -1 for x, 1 for y, you get -1 divided by 1, which is -1, and you see that we've got a slope of -1. And so from this, you can start seeing where if we were to choose a specific point as our initial value, we're going to get some sort of a function that's drawn on here. It turns out that this is a hyperbolic thing. You can kind of see the hyperbole in this. Notice how this gives us sort of the smile up top, and there's the corresponding frown on the bottom. And then on the left and right, we have the same kind of deal. So this one gives us a hyperbola, but regardless. let's go ahead and do the one that we're looking at. So let's look at logistic growth. So I need to choose values for K, and I need to choose values for L. I need to actually give something to Desmos or else it's not going to know what to do. So how about we'll let K be 0.1, just to have a number. And we're going to go ahead and multiply that to Y. And then we're going to also multiply that to L minus Y. So let's give ourselves a carrying capacity. So this way I don't have to adjust the scale of my screen. I'm just going to do 5 minus. Except that didn't do what I wanted it to do. Oh, there it goes. I think it was just slow. All right, so there is our slope field then for 0.1 times Y times 5 minus Y. All right, so let's just look at this slope field and talk about what this means in terms of, say, population growth and initial values and all that. So I'm going to go over here to where we're just positive, because this X, it's usually a time, and we're talking time from now. So we'll just look at from 0 on up. So the first thing I want you to notice is what happens if we're at Y equals 0. So Y equals 0 is down here. And notice that if you're here, you're always going to be here because the lines are horizontal. So you just keep moving to the right. And so if we start with a population of 0, we're going to stay 0. There is no growth rate. Okay, also, if we go to Y equals 5, notice that all of those are horizontal, and that's suggesting that we're going to stay at 5 the entire time. Well, basically, if you look at that differential equation, come back over here, plug in 5 for Y, you're going to get a derivative of 0, which means unchanging, you get a constant. So we actually call those places equilibrium values. Those are values for this differential equation that if we reach them, we are stuck there. We'll talk more about this later when we talk about, they're called autonomous differential equations. But those are equilibria. Those are places where we're going to actually be constant. Now, notice what happens if, say, we're bigger than 5. So let's say we had an initial condition of Y of 0 equals 6. So we're actually larger than our carrying capacity. And notice that up here, the slopes are all negative. I'll even pull it a little bit further down on our screen. See if we can see some more up here. But notice that all of these slopes are negative. So if we actually start up here, we're going to begin by dropping down. As we drop down, we're going to flatten. And so what we should expect if we have an initial condition up here is that we're going to kind of come down and approach 5 from above. If we're below 5 but above 0, notice that those slopes are all positive. And so we're going to see the same thing where we're going to increase until we approach 5. And notice that it starts flatter, gets steeper, and then flattens out again. We're going to be able to see that a little bit better, I think, if we zoom in, and I might try zooming in here in a second and play with this. All right, so there's our increasing and flattening out. If we had an initial condition where we started with a negative, obviously this doesn't make sense for like populations or anything like that, but let's say we started with a negative. Notice that these guys are all decreasing slopes. So if we were to start negative, we would just continue going negative and going away from 0. So these two equilibria, the 0 and the 5, both play very different roles. Notice that with 0, if you step off of 0, either way, you're going to move away from 0. If we're down negative, it's going to drop us. If we are a little bit above it, we're going to go up. And 5 is actually the opposite. If you were to step off of 5, either way, you get brought back to 5. It's a little bit bigger, it drops you back down. If it's a little bit smaller, it brings you up. So let me just show you what changes if we change some of these values. Obviously, if I change that carrying capacity, what we should see is that flattening out spot is going to change. So give it a second to readjust here. There we go. So now instead of that carrying capacity being at 5, it's up at 8. But we see the exact same structure as before. Bigger than 8, smaller than 8. We're going to come back towards 8. 0, we go away from it, right? We get the same general shape. So that's what L does. If I change my K, so we were at 0.1, let's make it 0.5. And notice what happens here. That was 0. Wait for it. There's 0.5. So what do you notice? What's the difference here?
It grows faster.
Yeah, now this is a faster rate. Look at how steep these are compared to what they were before when it was 0.1. So let me make it smaller than we saw before. Let's make it 0.05. And now notice that those are flatter as well. So that's why this K is a growth rate kind of idea. The bigger K is, the faster you're going to approach that carrying capacity. All right. So there's a reason I wanted to talk about this one today, other than the fact that it's a cool separable differential equation. But it's actually really, really applicable to what's going on in the world right now. With this COVID pandemic, what we're modeling isn't the population, but we're modeling the how many people are sick. And the number of people that are sick is growing logistically. There's going to be a carrying capacity because there's a maximum number of people who can get infected with COVID, right? It's the population of the earth. So what are we up to? Almost like 7 billion or something like that. But that's our max number. We're not going to go above that. And as we get closer to that number, the change in people infected is going to slow, right? And that should make sense, right? Because like, let's say 80% of the people are already infected. Well, you're not going to be running into a lot of uninfected people, right? And so there aren't a lot of uninfected people that can still get infected and so on. But anyway, so this is growing logistically. So you know the phrase we hear all the time, flattening the curve. They're not talking about flattening the logistic curve. The logistic curve looks like what it looks like. And I guess we never did really draw it, but it starts slow, goes up exponentially, and then flattens out, right? And that K value is just a matter of how steeply we get up there, right? So a big K brings us up fast. A slow K brings us up slowly. A small K brings us slowly. And so when they talk about flattening the curve, they're actually talking about flattening the derivative. If you look at the derivative of one of these things, it's got a hump. It kind of does this, right? Because we're always increasing, but there's a point of maximum increase and then it slows down. And when they say flatten the curve, they mean bring that hump down. If you bring that hump down, you're lowering the K. And so it's taking longer for us to reach that maximum value. And of course, the idea behind that from the science perspective, and not just science, I think the cultural, the societal perspective is twofold. One, by slowing it down, it's giving us more time to maybe come up with better testing, maybe we can create some sort of immunization, something like that. And so we're kind of buying ourselves some time. But then the other thing is it's keeping our medical system from being overwhelmed. Because obviously, as people get sick, they need to be treated. If we've got a large K, we're going to have lots of sick people really quickly. And we don't have the resources to take care of everybody. But if we can decrease that K and bring it out here, then people are still getting sick, right? It's not like this whole social distancing, this doesn't mean people aren't going to get sick, right? We're still going to get sick. I think I heard something like they think 75% of people are actually going to contract COVID at some point. So odds are you're still going to get it at some point. But hopefully we're doing it so that we're taking turns, so that we're not all getting it at the same time. So Barton doesn't all of a sudden have 10,000 people in there that are, you know, on deathbed. They've only got 10, and then another 10, and so on. So Monty, when you say it comes back now, people are getting it again. Is that what you mean? You can actually get COVID a second time. So you, if you build up antibodies, it's not actually enough to stop you from getting it again. All right, I hadn't heard that, which then of course makes this really interesting. And what it actually could be is like a mutation on the strain, because like that's what happens with the flu. When you get the flu and you get the flu again another time, you're actually not getting the same flu. You're getting something that's a little bit different that your body actually isn't immune to. But for other things, you know, like when as kids, you probably got immunization for like mumps. I know I did. And that one, yeah, we don't get mumps anymore because we've built up the immunities through that process. But anyway, it is kind of interesting that there's a lot of math behind this. And so what they're talking about in terms of this policy of having a stay at home and all that is really trying to use the math to their advantage. Thanks for sharing that, Monty. If you guys see on the chat, she just put a link to the article she was reading that was talking about how people can get it again. So, but anyway, so this logistic growth curve, what's kind of fun is you can play with this a lot. You can actually do all kinds of things to it to make it more realistic. Like, and I'm sure when we get there, we'll talk about this when we get to autonomous differential equations. But one thing that is a reality when it comes to population modeling is that not only is there usually a carrying capacity, there's usually also a threshold, a minimum number that you have to have, right? And that kind of makes sense. Like imagine, you know, we're talking about coyotes that are in Lake Tahoe. If that number drops too far, the population's going to die out. There aren't enough to actually breed and produce new ones and all that. And so you can create functions that has where there's a threshold, a minimum number, and also a carrying capacity. It involves basically just another fraction that you can split it apart. But it ends up getting kind of the same form. And so this can get a lot of fun. And then you get to fun things like, well, if we're talking about coyotes, they have to have other animals there because they eat the squirrels, right? So then we have to look at how squirrel population affects coyote population and vice versa. And then you get this great dance between the two. It ends up being cyclical, so you get some trig involved. And so population dynamics can actually be a really, really complex thing if we want to make it realistic. But even at a not totally basic, only exponential growth, but with at least some restrictions, you guys are at a point now where you can actually do the calculus. So Wes, you just asked, is there a minimum number for corona? Is there a threshold? I guarantee you there is. I don't know what it is. Obviously 0. Yes, there have to be at least some people in order to get it, but there is probably a minimum number. If our population were to drop so that, you know, there were only 1,000 people on Earth, we'd probably be able to socially distance ourselves enough that corona would not keep going, right? And I know 1,000 is probably a ridiculously small number, but there's going to be some point at which we can separate ourselves. But you're noticing, if you've been following along, that the people that, like, where it's really being a problem is in real concentrated population centers, where there are a lot of people in a small area, like New York City, you know, China, where it actually started in Wuhan province and stuff like that. It's just, it's really compact community, so high population density. And so there's plenty of resource for the corona. You know, are we going to see the same issue in places like Wyoming? Probably locally, you know, in like the towns in Wyoming. But if we're going to look at the people that are just out and about, they're much less likely. So anyway, so look at that. Real life applies to differential equations and vice versa. All right, so I'm going to show you Actually, I'm not. I'm going to call it a day because it's Friday, right? I mean, not that it really matters because tomorrow's still kind of the same. So we're going to go ahead and call this for today. But this was section 2.2. You are now good to do all the homeworks from separable equations. And what we're going to do next time is actually look at the existence and uniqueness. Like I've kind of been going along the lines of, yeah, we can find solutions. We need to talk about, can we find solutions? Are we guaranteed solutions? And if so, is there going to be only one? You've already noticed that there are times when there's not just one solution, like this one, right, where we got that logistic thing, and we also got y equals 0. So we'll talk about that, and then we'll kind of keep marching along in terms of different techniques. So I'm going to hit pause so that we can go off the record. Except when I say stop recording.